the fact that Bitcoin uses proof of work as its consensus mechanism. So we talked about the attacks that can happen on it. We also talked about writing smart contracts in Ethereum, but one of the things that I didn't mention is that Ethereum doesn't actually use proof of work. So originally, Ethereum used to also have a proof of work system very similar to Bitcoin, but it has now switched to something called proof of stake. And that's basically the main topic of this session. So let's start by talking what's wrong with proof of work. So the first thing that is wrong with proof of work is the energy inefficiency, right? So consider Bitcoin, for example. You have to constantly compute hashes in order to mine a new block. And people are computing millions of trillions of hashes. I mean, the numbers are so big now, I can't even fathom them. But then this is going to use a lot of electricity. It's, of course, costly. You need to invest in hardware. You need to pay for your electricity bills. In a lot of cases, you need a lot of cooling mechanisms and so on. So you have Bitcoin mining operations close to the North Pole, for example, because it's cheaper to cool. And this is basically not great, to say the least. And it has a catastrophic environmental impact because I think last time I checked, Bitcoin is using more electricity or more energy than the entire country of Argentina. And it's just not something that we would like to do. And the worst part is that this whole calculation, it's completely meaningless, right? So it's actually useless work. Of course, it helps with reaching consensus on the blockchain, but what else is computing hashes good for? Like we're just computing a bunch of hashes of randomly selected nonces in blocks. It's completely useless, right? But we also saw that this can affect the safety or security of the network. So we have a problem with centralization. This is the point that we come back to all the time in this course. The idea that you have two miners or two mining pools who have more than 50% of the entire hash power. So this goes against the whole promise of Bitcoin, that it was supposed to be a completely decentralized cryptocurrency. How is it decentralized if 2 or 3 people can control everything? And of course, we also saw the security issues, like 50% attacks and so on in the last session. So basically, if you want to attack Bitcoin, even assuming that you need 50% of the hash power, it's actually pretty easy to buy 50% of the hash power. Okay. It's easy in comparison with the amount of Bitcoin that is actually at stake. So because of these problems, people were looking into alternative mechanisms to reach consensus. So let's say I want to have the same concept of blockchain. So I have a bunch of blocks. Each block has a bunch of transactions in it. Each block points to the previous block. That's a blockchain. I just need a rule for extending the chain. I need a rule to say who can add new blocks. And that was the whole problem of consensus. And the way Nakamoto solved this in Bitcoin is by proof of work. It just says you have to compute hashes, and the first person who happens to find a matching hash, the first person who happens to find a block whose hash is smaller than some difficulty threshold gets to add the block to the blockchain, right? But effectively, this is like a randomized selection of miners. If you think about it, it's like I have these miners who are competing for creating the next block, and I'm technically choosing one of them at random. It's just that the probability of each miner being chosen is proportional to their computational power. It's proportional to the number of hashes that they can compute. So the idea in alternative consensus mechanisms is let's tie this probability of being chosen to something else. Let's say that instead of your probability of being able to add the next block being proportional to your hash power, it's proportional, let's say, to the amount of memory that you have, or it's proportional to the stake that you have in the currency, how many coins you have. So these things will give you proof of space and proof of stake. Now, I'm just going to mention proof of space really fast because mainly we're going to talk about other things, especially proof of stake, but let's talk about proof of space. Okay, what is proof of space? The idea is I don't want to use as much energy as is used in computing hashes in proof of work. So I want to have some sort of computation as before, but I want this computation to use a lot of space, a lot of memory, instead of using a lot of CPU or like hash power. Okay, so the basic idea is that we find a computational puzzle and this puzzle should have these properties. First of all, it should be easy to solve if you have a lot of memory, if given a lot of memory. Okay. And then it should be really hard to solve. And again, this is hard to solve in the same sense that, for example, hashes are hard to invert if you have little memory. Okay. Now, if we can have such a computational puzzle, then the miners no longer have to constantly compute hashes. Instead, they have to buy a lot of disks, let's say hard disks or SSDs or whatever, and then they have to store a lot of information so that when it comes time to mining, they can mine the next block easily. They can find the solution to the puzzle easily. And again, the idea is that we make it so that your probability of being the next one who can solve this puzzle is proportional to the amount of space or memory that you have allocated to this. Now, I'm not going to go into details of proof of space. Honestly, it's very complicated. I will give you some papers to read if you're interested in it. But let's just go back and see which of these problems will be solved by proof of space. Well, the energy inefficiency problem is pretty much solved, right? Because I don't have to constantly compute new stuff. But now it's replaced by a different problem, and the problem is the cost of hardware, right? So if I can add it here, cost of hardware. Now, the hardware that you use for proof of work is already expensive. Maybe you buy GPUs, maybe you buy ASICs, whatever hardware you're using, you have to pay something for it, of course, but it's not as expensive as disks. So if you go from proof of work to proof of space, your cost of hardware actually goes up. But now you don't really have much energy usage. You don't use much electricity. So in that sense, the energy efficiency portion is solved. Now, we can also kind of say that the environmental impact is solved, right? So let's call it, let's put this one here, environmental impact. Now, what is the main problem with proof of work? The main problem is that it uses a lot of electricity, it produces a lot of heat, it's bad for the environment, and so on. So if instead of constantly running GPUs and computing hashes, I just have a bunch of SSDs, they don't use much electricity. So the environmental impact is much smaller. Of course, there is still the environmental impact of actually producing those disks, right? And again, the problem here is that those disks are doing useless work. So it's a cheaper useless work, but it's still useless. You're filling up a bunch of disks with a bunch of random data so that you can compute some puzzle sooner so that you can add the next block. It's not useful for anyone. And it doesn't really affect the problems that we had with centralization and 50% attacks, right? Because what's the problem in centralization in Bitcoin? The problem is that it's cheaper to buy hash power than it is to buy Bitcoin itself. So if someone wants to do a 50% attack, they can just go and buy 50% of the hash power. It's of course very expensive, but at the same time, very cheap in comparison with the total value of Bitcoins in circulation. So now if I say that instead of mining using computational power, you're mining using space, nothing really changes fundamentally. Someone can just go out of their way and buy a lot of disks, right? So it doesn't solve these problems. But overall, it's a really good improvement over proof of work because at least we don't use as much electricity. But unfortunately, people didn't really adopt this. So as you know, Bitcoin is currently the biggest cryptocurrency. And it doesn't matter that we have better solutions. No one is using them. So there are actually smaller cryptocurrencies that are using proof of space, but they're very small. And it's just people know about Bitcoin. They don't know about these ones. Okay. What else can we do? Well, this one didn't solve the useless work part of it. So what if I take proof of work and I try to create proof of useful work? Now, what is the idea here? The idea is that, well, in proof of work, you need to solve a puzzle in order to add a new block. But these puzzles are meaningless. They're just inverting some hash function. What if instead I give you some meaningful puzzles, something that scientists actually care about, and I say whoever can solve this first gets to add the next block? So this is what we call proof of useful work. And there are many variants of it. So for example, there is a coin that uses protein folding. This is actually an NP-hard problem that is very important in drug discovery and so on. And they just say, well, if you can solve some instances of this problem, you can add new blocks. Okay. And then you also have hybrid approaches. So the idea in hybrid mining is that you can add new blocks either by solving a useful problem or by just doing normal proof of work, just doing the hash puzzle. And the way this works is that suppose I'm someone who has a real world problem. I first reduce that problem to a particular and fixed NP-complete problem. Let's say I reduce my problem to satisfiability. And then I can say, I can basically propose this problem as a problem for adding new blocks. So I can say, let's say adding each block in Bitcoin right now gives something like 3 Bitcoin as rewards. So we can just extend the Bitcoin model such that anyone else can come in and say, here's 3 Bitcoins for anyone who can solve this particular problem. And if they can solve the problem, then they get to also add a block. Now, this will also have all sorts of technical details. So for example, suppose that I have proposed the problem and you have solved it. You don't want to show the solution immediately because someone else might do a front-running attack on you and so on. So there are all sorts of difficulties in there. But that's the basic idea. The idea is that you do a kind of work that is useful to at least someone in the sense that they're willing to pay as much as a block reward for it. Okay. But again, these problems, these protocols, proof of useful work, they don't solve all of our problems, right? We still have the cost of hardware. We are still doing calculations. It has environmental impact. Now, you might argue that the work that we're doing is now useful, but in practice, you almost always run out of useful things to do. So people stop giving you problems, and then it has to just switch to the basic proof of work as a default mechanism whenever there is nothing to solve. Okay. And again, it doesn't really help you with centralization or 50% attacks. Okay. Now, the other thing we want to discuss today, and this is the most important one, is proof of stake. Okay. Now, philosophically speaking, the idea behind proof of stake is that money basically shows that you have done some work, right? Now, I know that we live in a capitalist system and this is not how things work, but in an idealized system, if you have money, it means that you have done some work to earn that money, right? So instead of asking for proof of work, I can just ask you to prove that you have some money. And I can use that for my mining. I can use that to add new blocks. Now, there are many different variants of proof of stake. We're going to talk about two of them. And actually, I'm going to only present one of them in detail because the other one is a 70-page paper that I will put on Canvas for you to read if you want to. It's really hard to make proof of stake work. Okay, so the first variant that I want to show you is the variant that is used by Peercoin, or also called PP coin. And this was actually the first proof of stake works in the real world. It's not entirely proof of stake. It's kind of a mixture of proof of work and proof of stake. Okay, so here's the idea. Let's say that I have my blockchain. These are the blocks that are already there. And let's say that I want to add a new block. Okay, so I wish to add this block. Now, what happens in Bitcoin? In Bitcoin, I have to solve a hash puzzle, and there is a fixed difficulty, right? So I have a block whose hash is less than or equal to some fixed threshold. Okay, so for example, I say that I have this D. I have to make sure that whatever block I want to add here, the hash of this block is less than or equal to D. And the idea in Bitcoin is that this difficulty D is the same for everyone, right? So we talked about this. Of course, it changes by time because we want to make sure that we get one block almost every 10 minutes. But at the end of the day, if all of these previous blocks are fixed and a bunch of miners are competing to add this next block, all of them are competing with the same difficulty. Okay, so the idea in Peercoin is basically, let's make life easier for rich people. Let's change the difficulty based on how much money you have. So if you have more money, of course, you're more trustworthy. So you get to solve an easier problem. Basically, your D will be bigger. If you have less money, we don't trust you as much because you're not really invested in this coin. Maybe you're an attacker. So we're going to ask you to solve a harder proof of work puzzle. Okay, but we have to find a way to really formalize this. And also the other issue is that what happens if someone has a lot of money? Should they just be able to add blocks over and over again? Not really. We want to give everyone a chance in some sense. So what Peercoin does is actually very interesting, and it's something that you can easily build on top of Bitcoin. It defines something called coin age. Now, what is coin age? Let's look at a transaction. So let's say I have, okay, sorry. Let's say I have a transaction, and we said that the Bitcoin model is the UTXO model. So every transaction has a bunch of inputs and it has a bunch of outputs, right? And we said that we call the outputs coins as well. So let's say that this transaction is paying one coin. It's not necessarily Bitcoin, whatever our current coin is. So one PP coin to Alice. And let's say that it's paying 2 coins to Bob. Okay. Now, when this transaction gets mined, it gets added to the blockchain. So I will have my blockchain here. And at some point, let's say at block 100, for example, I will have this transaction added to the blockchain by some point. Now, as soon as this transaction is added to the blockchain, I consider that as the time when these coins were created. And also at the time, as the time when the transaction inputs were destroyed, basically. Because again, we talked about this, the sum of outputs should be less than or equal to the sum of inputs and so on. So you can imagine that all the input coins are destroyed and all the output coins are created at the time of this transaction. Now, what is the time of this transaction? Well, we just use block numbers as time. Okay. So when this transaction happens, it creates two coins. One of them is worth 1, the other one is worth 2 units. And each of these coins will have an age of 0, basically. Now, as I add more blocks, the age of these coins increases. So for example, when I add another block, when I get a confirmation, the age of these coins increases by 1, and so on. So this is basically the same concept as the number of confirmations that you have after a particular transaction. And we talked about this. We said that we usually wait for 6 confirmations before we trust it. But now, instead of talking about whether I trust that this transaction will be reverted or not, let's just talk about the age of these coins. So if I have a bunch of other blocks here, each one of them increase the age of my coin. Okay. Now, the idea is that I want to say your stake in this currency is equal to the sum of the ages of all the coins that you have. So your stake in the currency is going to increase if you just hold some coins for longer. It's also going to increase if you make more money. So the stake is not just the number of coins that you have, it's the number of coins times their age. Okay, so basically your stake is going to be the sum over, let's say, all the coins that you own. And let's call this C of C.age times C.value. Okay. So originally, in block 100, when I have this transaction in there, both Alice and Bob have a stake of 0. But as soon as the next block is added, Alice has a stake of 1 and Bob has a stake of 2. And then when the next block is added, Alice has a stake of 2, Bob has a stake of 4, and so on. Okay. Now, how are you going to use your stake? Basically, the idea is that whenever you're mining and you want to add a new block, you not only do proof of work, but you also spend some of your coin age. Okay, not coinage, coin age. Okay, so previously, basically, when you had a block in Bitcoin, what was this block? The block had a bunch of transactions, right? And then it had a proof that it should be added to the blockchain, right? And what was this? This was like a solution to proof of work. But now in my blocks, I'm going to also do something else. I'm going to say you can also take some of the coins that you have and you can just transfer these coins to yourself. Okay, so now my blocks also have some input coins. Okay. And all of these coins should be owned by the current miner, of course. And then there is also an output coin or several output coins. And these are also paid to the same miner. Now, what's happening here? Why am I doing this? So, for example, I'm putting in, let's say, 1 Bitcoin, and I'm also taking out 1 Bitcoin. So what's the point? The point is that we said all the input coins are destroyed and all the output coins are created when this block is added. So whenever I'm doing this, I'm spending my coin age, right? The total age of my coins is going down. Okay. Now, finally, I'm going to have all of these things. But when I say solution to proof of work, the difficulty of this proof of work is going to depend on the amount of coins that I'm putting in. So if I'm spending a lot of coinage, then I can find a solution that has that is not that difficult, that has a large value of t, right? But if I'm not putting any coins, if I'm not spending any coinage, then I have to find a solution just like Bitcoin that has very hard difficulty. Okay, so that's the whole idea here. And of course, the exact formulas, you have to figure it out. You have to figure out like how much is, let's say, one coin block of age worth, like how much do you want to make the proof of work easier based on the amount of input coins. But you can read the white paper that they have, and it explains all the technical details. The important point here is that instead of just doing proof of work, you can now make your proof of work easier by spending some of your coinage. Okay. And of course, the idea is that if you have a bunch of coins, you would just keep them until their age becomes so much that it makes the proof of work puzzle easy for you. And then you just solve the proof of work puzzle very easily and add the input coins and output coins. So in practice, what's hoped to happen here is that after a while, the proof of work part becomes trivial, and no one really uses hash to solve the proof of work. Because after a while, you will have a lot of miners who just have a lot of coins. They have a lot of stake. They will have a lot of coinage every time, and they will mostly use their coinage here. And then they will have so many coins going into this block, or so much age going into this block, that finding this solution to proof of work would be basically trivial. It would be something that you can do easily on your laptop in like 1 second, right? So if you have, if you're putting enough stake in, then the proof of work becomes easy. And now everything is just like Bitcoin. So every time that I add a new block, everyone can verify. And the verification is also exactly like Bitcoin. So they have to verify that, of course, this is a valid block. It points to the last block. We have to make sure that all of the transactions in there are valid. But then everyone on the network can also check the ages of these input coins and basically sum the total value of these input coins, the total age. And based on that, they can know what the difficulty is going to be. And then they just check that the proof of work solution satisfies this particular difficulty constraint. So instead of just having a fixed difficulty for everyone on the network, the idea is the more coinage you put in, the easier the problem would be for you to solve. But again, everyone can verify it. And of course, we have the same rules as in Bitcoin. So if you have forks, you will look for the longest chain and so on. Okay, so this is the simplest case of proof of stake, but it's not really a pure proof of stake, right? It's like a hybrid of proof of work and proof of stake. But again, in practice, when the blockchain starts, because no one has any money at the beginning, and because remember, the way that we create new units of money is by mining. So initially, people are just going to do proof of work. And they're going to add blocks exactly like in Bitcoin. And each block is going to create new units of money that can be used in the system. But then after a while, I think in case of Peercoin, this took like 4 or 5 years. There will be enough money going around that it actually makes more sense to just do proof of stake and not do much proof of work. So effectively these days, the vast majority of the blocks in Peercoin are mined using proof of stake. So it's just a trick where you can bootstrap your blockchain using proof of work, but after a while, naturally people switch to proof of stake. Okay, let's go back. Now, which of these problems are solved by this protocol? So we don't have the problem of energy inefficiency in the sense that, well, after a while, at least it will be solved, right? So at the beginning, I'm doing proof of work. So at the beginning, I'm going to have all of the problems that proof of work had. But after a while, I'm going to switch to proof of stake. And then my proof of work part is going to be trivial. It's not going to use much energy, so my energy inefficiency problem is solved. The problem of cost of hardware is also similarly solved. You don't need to really have expensive hardware for computing hashes, or you don't need disk, you don't need any of that. When you have stake, if you have enough stake, you can just use a basic laptop to do mining. We're also not doing much useless work. Again, all of these things come with the caveat that after we switch from proof of work to proof of stake, we get these benefits, right? So we're not doing any useless work because we're not doing any work at all for creating proof of stake blocks. So it doesn't have environmental impacts. Now, here's the part where we have a problem. Well, will we have centralization? Now, at this point, centralization is no longer just about the amount of hash power that you have, but it's also about the total stake that you have in the currency. So if you want to be a pessimist or an economist, you would say that in capitalism, you will always have centralization. So there will be a point where very few people will own most of the currency and they will do all of the mining. But that's not the only issue here. The other issue is that we're not really getting rid of proof of work. So proof of work is still there. So this means that even when the vast majority of the network is using proof of stake to add new blocks, I can just come in and I can say, I'm a new miner. I don't have any coins in there. And I just want to try to mine new blocks using proof of work. Okay. Now, in their white paper, they actually tried to sell this as a feature, not a bug, because the idea is that if you're an outsider and you weren't participating in this currency before, you can actually come in and take part by just doing hashes for a while, and then you will have some stake. And they were also claiming that this helps with decentralization. But in practice, this means that the same attack that we saw in the last session can be applied here as well. Because fundamentally, when you have proof of work, someone can just go and buy a lot of hardware, and then they can get a majority of the hash power. Now, of course, in this case, it's not just the hash power that matters. It's hash power plus the stake that you have in your currency. But every time that you're using your stake, every time that you're using your coin age, you're getting new coins that have an age of 0, right? So it's not like you can just use proof of stake if an attacker is constantly using proof of work. They would be able to do the same attack that we've seen in the last session. It's just going to be costlier. So it doesn't really solve this problem. It kind of maybe solves this one, depending on how you define centralization. Okay. What if I want to have a pure proof of stake? Okay. And there are examples of this. So the most widely used examples are Ouroboros, which is a protocol that is used in the Cardano blockchain. And there is also Algorand. Now, these protocols are much more complicated than the level of this course, but I'm just going to give you the basic ideas behind them. And of course, you can just search for these 2 words on Google Scholar and you will find the papers. Okay, so what is the idea? The idea is that we want to extend what we had for proof of work. So we want to say every time a miner is chosen randomly, by the way, they don't use the word miner. They somehow, each currency likes to use a different word. So proof of stake currencies sometimes call it validator, sometimes they call it block producer. Proof of space people call it farming. I don't know why they do this. It's the same thing. It's just adding new blocks. So I'm just going to call all of it mining. Okay, it doesn't matter how you're doing it. The idea is that if you're adding a new block, you're a miner. So every time a miner should be chosen randomly for the next block, And we want this extra assumption that the probability of each miner being chosen should be proportional to their stake. And we're not going to do this whole coin age stuff here. We're just going to say, how many coins do you have? Like, what is the percentage of the coins that you own in this currency? That's your probability of being chosen to be a miner. Okay. So every time a miner is chosen randomly for the next block, and the probability is proportional to their stake. So this basically means one coin is like one ticket in a lottery. So we got back to all these protocols that we were talking about, and you were probably confused when I was talking about smart contracts and like random number generation and leader election and so on. Like, why do we care about this so much? This is why we care about them, because I want to choose the miner for the next block randomly. And basically, instead of saying that I choose the miner for the next block, you can think of this as choosing the coin that gets to mine the next block. So I have a bunch of coins. I'm choosing one of these coins uniformly at random, and then I'm saying the miner who owns this coin or the user who owns this coin gets to add the next block. Okay. So this is the idea in proof of stake. But I mean, it's a simple and elegant idea, but implementing it is much harder than you would think. Because of course, where does the randomness come from? And we've seen how hard it is to generate random numbers. And in all of the lectures that we were talking about random number generation, we were assuming that we already have a blockchain, right? So I was assuming that I have a working blockchain. And I was saying, assuming that I can write smart contracts, for example, in Solidity and run them on Ethereum, here's how I would generate a random number. I will have a bunch of people, I don't know, contribute some value, do VDF, blah, blah. But now we are one level lower in the architecture. We want to choose literally who gets to add the next block. We cannot just use the blockchain itself here. So that's why these protocols become much more interesting and much more complicated. But at the end of the day, the ideas that are used here for random number generation are very similar to the ideas we've already seen. So you have secret sharing, you have VDFs, you have like something else called VRFs, verifiable random functions, and so on. Okay, so how does this work? Basically, I'm going to look at time, and I'm going to divide my time into a bunch of epochs. So let's say I have something like this. This is the whole time. And this is the time where my blockchain started. And I'm going to say this is the first epoch, this is the second epoch, and so on. The third epoch. So each EI is an epoch. And oh, what happened with the internet connection? Why don't you see what I drew here? Okay, so I have my time and I have divided it into a bunch of epochs. And I'm going to go based on Cardano, which is actually one of the top 10 biggest cryptocurrencies. And it's one of the cryptocurrencies that uses pure proof of stake. Actually, it uses the Ouroboros protocol. So here, every epoch is almost 5 days. Okay. Now, again, these are numbers that you can choose for your own protocol. It doesn't really matter that much. You have to just make sure it's long enough or short enough for your needs. Okay. And then I'm going to say that every epoch is divided into a number of slots. So each EI consists of several slots. Now, actually in Cardano, the time difference between the slots is quite small. So every slot corresponds to almost 1 second, which is very different than Bitcoin, where every block comes after 10 minutes. And the idea is that in each slot, you can add a block. Okay. In each slot, we might add a block. Okay. Now, I say we might add a block because we can have empty slots. We can have slots. So you just think of a slot as 1 second. I can have a situation where this second I didn't find any blocks. Okay. But every second I'm going to have at most 1 block. And of course, every block is going to point to the previous block and so on, like all the normal things that we have in a blockchain. But remember, I want to choose the miner of the blocks, and I want to make sure that the probability is proportional to their stake. So I need some source of random number generation. I need to choose some people, form a committee, and this committee should generate random numbers. And these random numbers would tell me who the miners are. Okay. So this is what I'm going to do. I'm going to say each epoch has a committee. Okay. And usually in these protocols, you have a limit on the size of the committee. So I don't know. I have taken 100 people into my committee. And then the role of this committee is to just generate random numbers. So the committee generates random numbers. Now, how do they do it? Well, using any of the protocols that we have already seen for generation of random numbers, with the extra assumption that we don't have smart contracts. So whenever these members of committee want to communicate, they have to actually announce their messages to everyone. But we use the gossip protocol to send the messages from the members of committee to everyone else. So everything that the committee is doing is completely public. Everyone is seeing, if you're a member of the committee, what random value you're contributing and so on. So everyone can reach a consensus about the final random number that is generated, even though we don't have a smart contract. Okay. Now, this committee's job is to just generate random numbers. And well, they meet at the beginning of the epoch. So we're generating random numbers, let's say every 5 days. And then these random numbers would tell us who the miners in this epoch are going to be. So the committee has generated 1 random number for each slot. Okay. Now, again, to just simplify the matter, let's assume that all of the coins in my system have numbers. Okay. So let's say I have a total of n coins. And let's say these coins are numbered 0, 1 to n minus 1. Now, in practice, this is not how this works, but it's a simplifying assumption that gives you everything that you need to know about proof of stake. Okay. So for every slot, let's call it SI, we choose a random number. And this is RI, and this is a random number between 0 to n minus 1, and it's chosen uniformly at random. Okay, so at the beginning of the epoch, the committee is meeting, and they're basically choosing a random number for every slot. And then the idea is that the owner of this coin, and when I say the owner of this coin, I mean the owner of this coin at the beginning of the epoch. Okay, so the owner of this coin gets to be the miner for the block SI. Okay, whoever owns RI, and again, this is owning at the beginning of the epoch, because during the epoch I can also transfer money, but that wouldn't change my mining rights. Whoever owns the coin RI gets to add a block in the slot SI. Okay. Now, what's going to happen? Basically, I'm going to have these slots. Let's say in one epoch, I have slot 1, slot 2, slot 3, so on. And in each one of these, there is at most one person chosen who can add a block. So let's say that the person who was chosen for slot 1 added a block here. And then the person who's chosen for slot 2 can add a block. And of course, they would say that the previous block is this one, right? And so on. Now, let's say that the person at slot 3 is dishonest. Let's say this miner at slot 3, he sees that he's chosen to add the block according to the random number generation that was done at the beginning of this epoch, but he decides not to add a block. If he doesn't add a block, then the next guy at slot 4 creates a block and says, my previous block is this one, because that's the previous block that it has seen. So that's why I say every slot has at most one block. It can have more than one block. Now, again, let's say the miner that was chosen for slot 3 is dishonest, and they create 2 blocks or more blocks at slot 3. We will have the same situation as a fork in Bitcoin. The next guy gets to choose which one to extend, right? So this next miner decides that maybe I'm going to extend this one. And then we will just say that the longest chain is the consensus chain. And as long as a majority of the stakes are owned by honest miners, we will eventually reach consensus. There will be a longest chain. By the way, that's also the reason why our epochs are so much bigger than our slots, because we want to make sure that with very high probability in one epoch, we reach consensus. Okay. So this is the basic idea. The analysis is actually much more complicated. There is a lot of game theory and probability going on into this. And there are a lot of corner cases that you have to be careful about. So if you want to see all the details, read these 2 papers. But now we basically have a way of just using proof of stake. And this solves a lot of our problems. This basically solves all of the problems that we had here. So it's energy efficient. You don't need much hardware. It doesn't have much environmental impact. You're not doing useless work. You will have centralization as much as you will have it in capitalism. So if you have a bunch of people who own all the money, then there's nothing you can really do about that. And these kinds of majority attacks, the attacks that are used by having more than 50% of the hash power, wouldn't work here because you need more than 50% of the stake to do that kind of attack. Actually, again, there are tons of papers that show that it's not actually 50%, it's more like 30%. Even if you have 30%, there are some attacks that you can do. But anyway, this is much more expensive now because you have to actually own the coins. And if you own the coins, you hopefully don't want to crash the value of these coins that you own, right? Whereas if you just own hardware, you might want to crash Bitcoin. Okay, but we have a few remaining problems. One problem is the size of this committee. This committee should be small because we said that we don't have smart contracts. So when we're doing the random number generation, they're just going to use the underlying gossip protocol to send messages. So whenever a member of the committee wants to send one message, they have to send it to the entire network. So I cannot have a committee that has 1 million nodes in it, because that kind of committee would need to send 1 million messages, and then everyone will be stuck on the network. So I have to choose a committee somehow. And the way I choose a committee is also random. So I pick my committee also randomly, and I pick it in the same way as picking the block miners. So basically here, instead of saying that the committee generates random numbers and we have one random number for each slot, I say that additionally, we have random numbers that would tell us who's on the next committee for the next epoch. So the current committee generates random numbers, but it generates random numbers for the miners, but also generates random numbers that tell us who's going to be on the next committee. Now, one fundamental problem is, what do you do at the first epoch? Who's on the committee in the first epoch? And do you trust those people? Because you can see that if I have some sort of centralization at the beginning, let's say that I don't know, the Cardano Foundation, for example. By the way, Cardano Foundation, great people. I have nothing against them. But let's say I've started my epoch, and initially I'm saying that I have 100 coins and all of those coins belong to me. So I'm going to be the committee in the first epoch, and I'm going to be the miners in the first epoch. So instead of generating random numbers for the first epoch, I can just cheat, right? I can make sure that whatever I'm doing, I will remain, I will have all of the committee in the second epoch. Basically, I will have control of the committee. And then if I have control of the committee in the second epoch, I make sure that I have control of the committee in the next epoch, and so on. So you need a way of bootstrapping this. And the solution to this is that you go to a different blockchain that already exists, and you generate the randomness for your first epoch, for example, on a proof of work blockchain like Ethereum, which was proof of work initially, right? As long as you have an open randomness for the first epoch and you make sure that no one has a monopoly here, then afterwards you're fine. Because remember, when we were generating random numbers, all I wanted in order to have an output that was uniformly distributed is to have just one honest member. So as long as the committee has at least one honest member, we're fine. Okay, and again, there is a probabilistic analysis that goes into that, like what is the probability that everyone in the committee is dishonest? Assuming that a majority of the stake is held by honest participants, actually the probability is very low, because the committee would usually be 100 people. And let's say that half of the stake is honest. If half of the stake is honest, the probability that all 100 people on the committee are dishonest is like 1/2 to the power of 100, which is super small, right? And then again, we've seen in random number generation lectures that even if I have one honest participant, the final random number is trustworthy. So this is how proof of stake works. I'll see you tomorrow for the last session of the course.